Alrighty. So before moving on from intersections, I want to discuss a few applications. So first application would be okay, so let me see. Applications. So I'm just gonna sketch some things over here. So first is tangent fields on manifolds. So maybe you've heard the fact that like on a sphere, you can draw a tangent vector field, but this tangent vector field cannot be everywhere non-vanishing. In particular, it should have, it turns out that it has to have at least 2 points at which it vanishes, or a point in multiplicity too. On a torus, however, you can have vector fields which don't vanish, just like this thing going around. Turns out on a higher genus surface, again, you have to have some points at which vector fields vanish. So one way that you can prove this is a pretty clever application of intersection theory. And so let's say that you have a manifold M, and you have a vector field V on M. Okay, so we're gonna interpret this vector field as some sort of infinitesimal deformation of M, and sort of see how this gives us information about the vector field. So the idea is like last time we looked at CP2, and in CP2 what happens is like you have like the plane, you have the plane, and if you have like a line, then what you can do is you can like sort of infinitesimally deform the line, and then see where these two intersect with each other, and that'll give you information about like the normal bundle of this first line, because a section of the normal bundle essentially corresponds to an infinitesimal deformation of it. So we can do a similar idea over here, where we can embed M inside its product by the diagonal. So this will be M cross M, and we're embedding M as a diagonal over here. So over here we have the tangent part of M and the normal part of M. So we have, I'll call T diagonal, so T delta, and N delta. And I claim that at every point, T P delta, so the tangent, the vector space to this submanifold is isomorphic to NP delta, the normal component. And the way this isomorphism works is TP delta essentially corresponds to all vectors which have the same component in the horizontal and vertical directions. So this will correspond to vector search with v comma v. And you can send this to the vector v comma minus v, and then that'll be in this normal bundle part. So a tangent vector field, you can interpret that as a bunch of tangent vectors on your manifold, which using this isomorphism you can convert into normal vectors on the manifold. And then what you can do is you can sort of like flow this manifold along the normal vector field and come up with a little infinitesimal deformation of this. And you can sort of convince yourself that the points, maybe I shouldn't, but that can be more something like this. The points at which this manifold and its little infinitesimal deformation intersect corresponds to the points at which the tangent vector, normal vector field, and hence the tangent vector field vanish. And so you reduce this problem of looking at how many points a tangent vector field vanishes at to this problem of computing some sort of intersection of the manifold with a little deformation of itself. And you can compute this out. And I'll just state the theorem, which is called the Lefschetz fixed point formula. Maybe we'll do this on a problem set later. But then this implies that the number of vanishing points, again, with some sort of a sign according to intersection multiplicity, which can also be understood in terms of the vector field itself, is equal to, turns out, the Euler characteristic of your manifold. So a cool consequence of this is that if you know a little about Lie groups, Then a lead group is a group that's also manifold, like we talked about RP3, for example. And what that allows you to do is essentially take a vector at one point, and then apply some group element G, and then take that vector to another point. So what this means is that if you have a non-vanishing vector just at a single point of the identity, then using this you can get vectors everywhere else. So that means that every Lie group has a non-vanishing vector field. And this implies that the Euler characteristic of this Lie group has to be 0 because of this theorem. And by this is called the Poincare-Hopf theorem, one of my favorite theorems. And this implies that, for example, for surfaces, the torus is the only group, which you know that the torus can be made into a group because S1 plus S1, but it turns out that it can be the only one because of this topological obstruction. And if you're not convinced of sort of this self-intersection stuff, it might seem kind of wonky. One thing that you can imagine is like S2 cross S2. What you can do is you can take like a sphere, and the way I like to imagine this is like putting a sphere at every point over here. And then, for example, so a vector field then corresponds to a little deformation of the sphere. So you can show that the diagonal in this picture, it means that if you have like this point, then on the sphere attached to the point, you're going to want to go the outermost on the little sphere attached at that point. So the diagonal is actually going to look like this sort of outermost guy. And if you, for example, so that is the diagonal. And if you take this vector field which sort of points down, so it's sort of like the gradient of the height function, then you can show that if you sort of flow along these guys, then this picture is actually going to squeeze this sphere a little bit. And so what will happen is that it doesn't intersect itself except at these 2 points. So you can sort of actually kind of see this sort of intersection of the infinitesimal deformation with itself. So that's application 1. Application 2, this is going to be even more sketched out. This is something called the degree genus formula. This is a sort of a surprising thing. So if you have some polynomial f of x, y to 0 on CP2, then this is a sort of something that locally looks one-dimensional, but one-dimensional complex. So it looks like a surface. So it might be a sphere, it might be a torus, and so on and so forth. So this corresponds to, turns out, degree 1 and 2. So degree 1 is a line, which you compact by 1 point to get a sphere. Degree 2 corresponds to a conic, which it turns out you have to add 2 points at infinity and then you get a sphere. This guy corresponds to degree 3. And so you might ask, what should a genus 2 surface correspond to? And it turns out that you can't find any polynomial which is a genus 2 surface. So this is an interesting idea. What you do is you can think of this guy as like, here's your CP2, and you can think of your surface, let's call it S, as being embedded inside here. And so inside this, CP2 is real 4-dimensional. And so what you have, or complex 2-dimensional. So what you have is you have the tangent part to every point. So this is like TPS. And then you have the normal part, so NPS. And I guess this picture is way too messy to understand if you didn't hear me say that just now. But you have a tangent part and you have a normal part. And what you have is that TPS plus NPS is isomorphic to the tangent space of CP2. So what this is saying is you're essentially decomposing the tangent space of the projective space into the tangent space of the surface and the normal space of the surface. And this is analogous to what happens in R3, for example. If you have a sphere in R3, then you have the tangent plane, then you have the normal line, and together they form the R3 that's embedded in. So we can do some stuff with this. What we can do is we can consider, again, vector fields, except the vector fields with values in TPS, NPS, and TPC. And maybe using some notation which hopefully we did cover Turing process near the end, but if not, then I'll just sort of say C1 of any of these guys is going to be, quote unquote, the number of points at which generic section matches. I think this is, I guess, it shouldn't really be points. It should be really co-dimension one spaces. So for example, C1 of the tangent space we just showed is 2 minus 2g, which is the Euler characteristic of the surface. Does anyone see maybe what?
Wait, how do we show?
That was because of this calculation.
Oh, I see.
Yeah, if you take a vector field of the tangent space is something intrinsic to your surface, right? So it doesn't matter how it's embedded. But the normal space is. So does anyone have a guess as to what this is called the first Turing class, as to what the first Turing class of the normal space is going to look like? And I'll give you a hint. You can think of it also as like deforming your surface a little bit and then look at the number of points of intersection. Yeah.
Wait. Can you re-explain what you mean by the number of co-dimensional spaces of which a generic section vanishes?
Yeah, so for example, I guess the thing is like here it's a complex space. So what? Okay, so everything here we're considering is, I guess I should also say co-dimensional one over C. What happens is you have like, we talked a little bit about this last week, where you have like a space which is like above every point you have some vector space, right? And I informally said this is what a vector bundle is. So if you consider like a section of this, and you consider the zeros, okay, so you canonically have a zero section, which associates to every fiber the zero. And you have, if you have any other section, then this will be some other vector in your vector space. And so one way that you can interpret this is you're looking at the intersection of these two guys. And this will essentially be let's see. So each of so if your vector bundle has rank k, which remember means that each vector space is k-dimensional, then each of these guys is codimension k in the vector bundle E. So if you take the intersection of those two, then it'll be codimension k on the zero section itself as well. So this is something you can show, like if you have something which is in some ambient space, and so let's say this is M1, and let's say that this is M2, and the ambient space is N, and let's say M2 is codimension k in N, then this implies that M1 intersect M2 is codimension k in M1. So I guess this is still wrong. I mean, I'm not gonna formally say what a Turing class is, but essentially what I'm trying to say is like, over here you have a complex line bundle for the tangent space and the normal space, right? Because they're both one-dimensional. So, because the tangent space is two real dimensional, which is one complex dimension, and the normal space has to be the complement of that, which is also one complex dimension. So this is saying that if you deform that a little bit, then you can count the number of points at which it intersects the zero section, which is the base manifold itself. And then that'll define a codimension 1 guy on your zero section. So it's like what we did up here, where we deformed it a little bit and counted the number of points in the section. So over here, it's a similar thing. The normal bundle, if you want to compute the Turing class, you should think of like deforming your thing a little bit and counting the number of points of intersection. So if you do that for a degree D hypersurface, what should you get?
For degree 1, you get 1.
1, yep.
For degree 2, you get 4.
Yep.
So squared.
Yeah, so what happens if you deform, like for example, you might have something like f of x, y, right? And then you sort of like deform this a little bit to f prime, or I guess f tilde of x, y. And each of these will be degree d's. So essentially what we're counting is the number of points of intersection of these two, so it's going to be d squared. Does that make sense? So it's like you're deforming this torus inside CP2 a little bit, and you're counting the number of points of intersection of the torus with itself, and that's related to the degree of the polynomial that defines the torus. And the third thing that we'll need is, I guess this is where the definition of Turing class is a bit iffy, but I'll just say that for now, the Turing class of TP CP2 restricted to S turns out to be equal to 3D. And the reason for this is you can show that if you take a vector field of CP2, then the zero section, this will turn out to be codimension 1, and this is a degree 3 hypersurface. You can show that this is true. This is through something called the Euler sequence. I'm just naming some words here in case you want to Google it. I'm not going to explain this too much. But then if you so this is a sort of the Turing class of CP2, or the tangent bundle to CP2. But then if you want to restrict this to S, then this is the intersection of S with a degree 3 hypersurface. Because if you like look at the zero locus of something restricted, what you have is like some degree 3 hypersurface, which is the zero locus of tangent field. And if you want to look at the restriction of this to the surface itself, then it'll be essentially counting the points of intersection with the surface. This may seem a bit, and maybe, hopefully we will justify this later, but it's going to be equal to 3D. Just to give you a sense of what's going on.
So on vibes, why is the zero section a degree 3 hypersurface?
This is something you have to compute. It's something that you can do using the Euler sequence. The Euler sequence essentially takes, it's because CP2 is C3 modulo scaling. That's where the 3 comes from.
But roughly speaking, we're considering the tangent bundle of CP2.
Yep.
And what are we doing to it?
So if you take a vector field in the tangent bundle, then you look at the zero section, so where you have 0 vectors, then that will turn out to be a degree 3 hypersurface in general. So it turns out that it looks like a torus.
Oh, by zero section you mean like the vanishing locus?
Vanishing locus, yeah.
Oh, okay.
Sorry, yeah, I shouldn't have said zero. zero locus
I see.
of the section. Yeah. So then again, maybe this won't quite make sense right now, but because this is true, it turns out that 3D is equal to d squared plus 2 minus 2g, or in other words, g is equal to d minus 1 times d minus 2 over 2, which you can also write as minus 1 choose 2. And so it turns out that the degree of your polynomial that defines an equation, assuming that it's a non-singular curve, has to have genus g, which is kind of interesting. And we sort of got this through some sort of roughly some sort of intersection type argument. So what this means is, like, if you look at what the value is for d and g, so if you take 1, you get 0, as you expect. If you take 2, still get 0. If you take 3, you get 2 choose 2, which is 1, which is why you might have heard that elliptic curve, which is a torus, is a solution to a degree 3 polynomial. If you do 4, you get 3 choose 2, which is 3. So you actually skip genus 2, so you actually can't embed a genus 2 surface in a non-singular way into the complex projective space as the solution to polynomials, which is kind of a strange statement to make, but it turns out to be
So
true.
does that mean also there's no complex structure on a genus 2 surface?
No, you can embed it into CP3.
Oh, CP2.
Yeah, you can embed it into CP2, but it turns out you can embed it to higher things. Yeah. Okay, cool. So that's all I want to say. Oh, wait, no. A few more words and applications.
Can any genus G surface be embedded into CP3?
I think so.
Is it like a Whitney embedding theorem for complex
Yes.
manifolds?
We can talk about this later. Other applications include this. So let's say that you have a 4n dimensional manifold M. Then what happens is, y the Vetch product, you go from H2n cross H2n to H4n, which you end up with R. And so you should think about these as 2n dimensional submanifolds. And this composite map, this is integration, and this composite map as the intersection pairing. And so why 4n? Well, obviously you need something even dimensional so that, like, you have the same exponent up here. But when you have it 4n, then if you take omega wedge eta, you're going to get eta wedge omega. Because you multiply it by -1 to the power of 2n squared. If it was just a 2n dimensional manifold, then you pick up a negative sign. So in this case, this is equal to 1. And so this is a symmetric thing. So you get some sort of a symmetric bilinear pairing on H2n. And this is actually pretty powerful because it turns out that pairing on H2 of some manifold, 4-dimensional manifold, and so I'm not talking about integer cohomology here, but to state the theorem correctly, I'll state with integer cohomology. This pairing actually has a lot of information in it, because if M is simply connected, then it turns out that this pairing that I just defined here, the intersection pairing, classifies them up to homeomorphism.
Your manifold?
Yeah, so simply connected for. And it turns out that for every intersection pairing, there exists one or two, I'm pretty sure, manifolds with that. And so,
For general 2n unique
no,
or 4n?
dimension equals 4.
Oh.
So this is a 4-dimensional story. So this is like some technicality came with this where like, okay, we're trying to prove like Poincare conjecture. It was proven in dimensions 5 or higher. It wasn't proven in dimension 4 for a while, and the reason is because for some technical reason you have like you have a disk embedded into a 4-dimensional manifold, then the disk can intersect itself. If you're in dimension 5 or higher, then it turns out you can like deform the disk a little bit because the dimension count is pretty small. So you can remove all intersections and you use something called like the Whitney sliding. I think it's like the Whitney sliding trick, whatever, to remove some sort of intersections and then do some sort of Morse theory on this, which are just some words. But the point is that this guy is annoying and made Poincare conjecture hard in dimension 4 for a long time. So the order in which Poincare conjecture was proven was it was proven in dimensions 5 and higher first, and then it was proven in dimension 4, and then recently in dimension 3. So this was, the way to fix this was done by Friedman. So this theorem can be due to Friedman. And it turns out that you have some later work, Donaldson. There are other ways to do this now, but Donaldson showed that by solving some differential equations called Yang-Mills / anti-self-dual equations, they're called, on 4 manifolds, you can show that because it's easy to check when 2 manifolds are homeomorphic, you just have to check their intersection pairings are the same. Through some very careful analysis, you can check that some solutions to differential equations are going to be different. So you can find manifolds which are homeomorphic, but not diffeomorphic. And so 4-dimensional things are weird. What this even means is like strange. So that's one thing. Another thing, that's additional application 1. Additional application 2 is surfaces. You also have a pairing on H1 in a similar fashion, except this one is antisymmetric. And so what this does is it induces what's called a symplectic form on H1, which essentially just means this. It's a bilinear pairing, which is antisymmetric. And what happens is if you look at, there's something called the mapping class group of a surface. And this is equal to the homeomorphisms modulo those which are isotopic to identity. Okay, so what does this mean? So if you take something like a torus, then you can like sort of choose some homomorphism of this torus that sort of like flows things around, right? But there are some homomorphisms that cannot be obtained by flowing things around. So for example, you have something called a Dane twist. And so what you do here is you take your surface and you choose some circle over here and you cut open along the circle and then you rotate one side by 2 pi and then you glue it back. And so what happens here is like if you have something which goes around once this way, then it'll end up going sort of down and then come back up. And this means that this Dane twist cannot be obtained as like sort of flowing along these guys. And so this is sort of some sort of a discrete group which measures these homeomorphisms that cannot be continuously performed to the identity.
How big is it usually? Like how big is it?
Right, so I'll give you an example. E.g. T2 for T2, the mapping class group is equal to SL2Z. And you can see this because T2 is equal to R2 modulo lattice. So this is essentially SL2Z is the automorphisms of lattice. And so you asked a good question, how big is this? So it turns out that in general, the mapping class group is going to act on H1, right? Because of what I did over here, it sort of like twists the circles. So what that means is it gives an automorphism on this vector space, but it preserves the pairing. And again, we can talk about things with integer coefficients, which I won't talk about what that means. Essentially, integer coefficients, you can think of that as like cohomology classes which come from Tom classes. So Tom classes sort of integrate to one along these cochains, or along these chains, and so they're sort of more integral than your normal differential forms. And so what this means is that you have a map from the mapping class group to was SP, this has rank 2G, so this will be SP 2G. So this is things which preserve, matrices which preserve the symplectic form. So you should think of this as an analog to the orthogonal group, but instead of preserving a symmetric form, it preserves an anti-symmetric form. And it turns out that this guy, this map, has, I think, I might be quoting this wrong, but I'm pretty sure it has finite kernel and finite coca. And so what that means is like, it's very close to this sort of integral matrix group in size. So yeah, this sort of answers your question. So this is another sort of one way that you can use intersections in an interesting way. Questions on any of the applications that I stated so far? Otherwise,
This is the mapping class group of any surface of genus G.
yes,
It's basically the symplectic group.
it's very close to symplectic.
Where this 2G means that's the dimension.
That's the rank. Yeah. It's like this is inside M2G by 2G matrices.
Right. So it's the dimension of the matrix.
Yeah. Okay.
So you said the self-intersection number is a first Chern class of the normal line.
Yeah. Yeah. I'll talk about Chern classes hopefully at the end of the term. Yeah, we'll see that we can get Chern classes from differential forms. That'll be interesting. But anyways, so now we're gonna forget about all of this, and we're gonna start talking about something quite exciting. This is what I've been sort of waiting for in the class. Finally, we talked about some rudiments of Hodge. So, I mean, this is something where it's like, I won't go into the detail where it's like you'll understand what the Hodge conjecture means, and usually Hodge theory is like something where the complex numbers as well. So it won't be like super deep, but like compared to what we've been doing, it'll be like really interesting. And also these ideas for not being too difficult show up quite a bit. So if you do some sort of geometry. So I thought it'd be nice to discuss it in this class because I feel like people don't usually talk about differential forms when they do cohomology, and even when they do, I guess maybe they don't really mention this. And we'll use this to prove two theorems. So theorems, which I'll discuss in a moment, is Poincare duality and uniformity. So if you read Bottom 2, it kind of proves this using sort of induction thing with Marviator, similar to what we did at the end of last lecture, which is fine, but I kind of wish
It
that...
proves Poincare duality, you mean?
Hmm?
It proves Poincare duality with Marviator?
Yeah, Poincare duality and Knuth formula.
By patching.
Yeah, by patching together things on over which it's trivial and showing that it holds in general. But in my opinion, like if you're gonna do homology with differential forms, then like Hodge theory should be like the way to do it, because it's like something that's like special to differential forms, and it's like really quite a nice way of proving these statements. And yeah, so that's what I'm gonna hope to do. I'm gonna first talk about these theorems a little bit, and sort of talk about some intuition behind them, and then discuss how to prove it, and in the process define what Hodge classes are, or harmonic classes, or whatever. Okay, so let's first talk about Knuth formula. So, or actually, let's first do this. Table of cohomology. So let's start the cohomology of some places that we know. So if we have surface of genus G, then the cohomology of this is going to look like essentially I write dimension for cohomology. So dimension for the surface is going to look like 1 to G1, right? Dimension of H star CPN. We computed this as well. This is going to be 1, 0, 1, 0, 0, 1. This is in like I equals 0, I equals 1, I equals 2, so on and so forth. By the way, this pattern corresponds, we saw that in 2 dimensions, the sky corresponds to the hyperplane. It turns out that in every other dimension, it corresponds to like codimension K hyperplanes. So you can sort of do find generalizations of Jesus theorem using this cohomology guy.
Wait, sorry, you mean like intersecting hypers, like hyperplanes?
Yeah, so you can show that, for example, the generator for H2 will correspond to the Tom class of a hyperplane. And H4 will be the same thing of a codimension 2 plane, and so on and so forth. Yeah, so there's that. In particular, if you do this guy for S1, then you're going to get 1, 1, right? And if you do it for T2, you're going to get 1, 2, 1. I think there's another problem which we didn't go over, but as you do for Tn, and you're going to find that it looks like 1, 3, 3, 1, 1, 4, 6, 4, 1, and you can kind of see the pattern. And another interesting thing is going to be, like if you do the dimension of H star of SG cross SG, so the product of the surface of itself, I think what you should get is 1 4G squared plus 1, I don't know, 4G 1, and then some other things. So you can show all of these through through Marviators, and some computations. Some interesting things that you notice is like it seems like dimension of HK of M is the same as the dimension of Hn minus K of M. So that's first observation. And second observation is maybe you can see it through here or through here, which is that HK of M cross N is equal to the direct sum over I plus j equals k of hi of m times hj of n. So I guess this is a wide dimension counts, like these equalities hold, but it's sort of saying something a bit stronger, which is that they should hold on the level of vector spaces as well. Where you replace this you replace like addition with the sum and multiplication with the tensor product. Anyone not familiar with tensor product? Okay, so just to give like a quick overview, what tensor product essentially means is that you're multiplying things of two vector spaces. Okay, so what does this mean? Let's say that you have V tensor W. So elements of this are going to look like V1 tensor W1 plus 3V2 tensor W2. And so you can have like formal linear combinations of just products of these guys. And the idea is that what is a vector space? You have addition and scaling, but no multiplication, right? So you can't, in general, multiply vectors. So this tensor product sort of fixes that by saying that you can multiply things from V and W, except what you end up with is the thing in your output is neither V nor W, it's this third vector space, which is V tensor W. And this vector space is essentially just formal linear combinations of these guys, satisfying like the distributivity property, for example. So what that means is like V1 plus V2 tensor W to V1 tensor W plus V2 tensor W. So when you see this tensor symbol, just think like it means multiplication. Yeah. And so you can check that this is dimension K, this is dimension L, and this guy will have dimension KL. Cool. So this theorem is called Poincare duality, and this theorem is called the Knuth theorem. Okay, so let's discuss each of these in some detail. So, wow. So let's see here, Poincare duality. The idea is you can intersect codimension K and codimension n minus K submanifolds. Right? So this will correspond to something inside. So the Tom classes, which we went over, and to give you a little refresher, the Tom classes just means that if you have a circle over here, then it's going to be some differential form, which is concentrated in the perpendicular direction, sort of measures things going perpendicular to it. The Tom class is going to live inside hk over here and hn minus k over here. And so this intersection pairing, as I've said before, will give you some map from these two to hn. And in all the cases that we've seen so far, this is isomorphic to R, where the isomorphism is given by the integral, or the entire manifold. And so you get a pairing like this. And so Poincare duality says that the pairing is non-degenerate. And so what this means is that for all omega inside hk, you can find an eta inside hn minus k such that the integral of omega wedge eta for the entire manifold M is non-zero. So this is sort of a weaker version of an interesting geometric statement, which says that geometrically, if you have a submanifold which does not bound, so that means that it's a submanifold which you can't sort of contract to a point or is the boundary of some other thing, then that implies that there exists another one which intersects it non-zero number of times. Okay.
Both closed.
Yes. Yeah. So this is kind of
Are they
interesting.
inside a closed manifold too?
Yeah. So everything is happening inside some ambient manifold. So this is kind of interesting because it says like if you have something which is non-trivial, you can find something else which is non-trivial which creates it, which is not obviously. So what we'll and so this relates to this statement why Tom calls this. Okay. So what we'll prove is slightly weaker. All we'll do is we'll show that if we have a Tom class, then we can find a cohomology class opposite to it that pairs non-trivial with it. That doesn't mean that the cohomology class has to come from it. The other cohomology class has to also come from the Tom class. So it'll be slightly weaker than the statement, but this is like a geometric sort of idea that we're trying to get to. And so you can maybe see that this is like highly non-trivial. So let's see. Yeah. And then the idea for the Kunath one is that if you have, for example, a torus, you can consider this as a circle cross a circle. And so the idea is that geometrically again, k-dimensional submanifold of M cross N maybe I shouldn't say it like this. If you have so this is M, this is N. Let's say that you have S inside M and P inside N, which is dimension K, this is dimension L. Then S cross T inside M cross N is a K plus L dimensional submanifold. And moreover, if this is not the boundary of something and this is not the boundary of something, then the product will also not be a boundary of something. So then we can hope that we get all homology, which remember that this is this H lower star thing that I talked about earlier, classes this way. In other words, if we have something which is non-contractible, then it's a formal linear combination of things which come from something down here times something up here. So in this case, if you have a non-contractible circle, then that corresponds to this circle down here plus this point over here. And then in cohomology language, let's say that you have forms omega inside hk of m and eta inside hl of n, then you would hope that omega wedge eta is gonna be inside hk plus l of m, and hope is that you can get all of hk plus l like this.
And how do you get the like linear independent? Like, isn't there that dual part? Like the rank is the sum of the.
Yeah. So there's two issues with this. Two issues. The first is you're not sure if you get everything, right? So you're not sure that like things of this form will be this whole dimensional space. And the second is not sure if omega non-zero and eta non-zero implies omega wedge eta non-zero, or more generally, linear independence. Eric, could I get the charger for the iPad? So yeah, so you have these two issues, which may cause this sort of a decomposition that I wrote up here to fail. But the hope is that you would be able to get everything through these points. And that's where this sort of tensor product comes from. Again, you should like just think of it as like you're like just multiplying this omega and eta together. Except a priori they're living on different spaces, but then like once you what I mean by this omega wedge eta, by the way, is you sort of pull it back to the product manifold via the projection mappings. And so if you have something which is like omega, something which is like omega over here and eta over here, then omega wedge eta just means that unlike the parts which come from down here, it's omega, and on the parts which come from up here, it will be eta. Does that make sense? Okay, so these are two theorems which we would like to prove. And in my opinion, like if you're gonna do round cohomology, the way to do these is to do Hodge theory. So yeah, over here we have some like difficulties. Over here, like these are the difficulties. Over here we have the difficulty that we not sure if the dual exists, right? And by the way, this is also like a sort of an interesting statement. This says that if you have, we showed that if you have a submanifold, then we get a Tom class from it. And we showed that the Tom class was a cohomology class, but by showing that d of it is equal to 0 by construction. But that doesn't mean that the cohomology class is non-zero. Because it could be equivalent to 0 under, which means that the differential form could be exact once you look at your big manifold. So what this will show is that if your manifold itself is non-contractible, then the Tom class is non-zero. So this sort of gives you a test, for example, to see if a manifold is non-contractible. I will say also, what we're proving is slightly weaker, but can be made the geometric statement if working over Z, which we aren't doing, but whatever. Okay, so solution two problems. Okay, we have about a few minutes. So what we'll do is we'll find special representatives of multiplexes. So we saw last week through this problem of that thing about links that you can have a homology class that has multiple representatives, and this is sometimes a useful thing because it allows you to equate two things which do not seem similar a priori. But this causes an issue over here because this problem, for example, of showing that two non-zero things wedged to a non-zero thing, if we had like sort of some special representatives, the idea is that if this is the special representative which is non-zero and this is also special representative that is non-zero, and we show that they wedge to the special representative on the product manifold, then the special representative of the zero cohomology class will be the zero differential form. So if we can show that this special representative is non-zero, which will happen if both of these are non-zero, then we show that the wedge part is automatically non-zero. So if we can find special representatives, then we can solve both of these issues. And we can also, turns out, explicitly find this rule statement. Cool, so what will these special representatives look like? So far, we've seen two types of classes. So the first is Tom/Bumpy classes. So my favorite guys, things which are concentrated near some submanifold. And second is sort of a more distributed class. So we saw some examples in the first week coming from electromagnetism, things which are sort of uniformly spread out. Or on the sphere, we saw that if you take the area form, then this will sort of be uniform on the sphere. And sort of the corresponding thing over here is like this Tom class, which is like sort of maybe concentrated near a point. So far we've talked about how to construct these guys, and so today we're going to talk about these more equally like sort of spread out classes a bit more. What does it mean for a class to be uniform? Again, so this is an interesting question because, for example, we have this class that we talked about. Again, like these should be differential forms. This should be really d theta, but Hausdorff vector fields are cheap. But everything that we've been dealing with so far is really topological sort of a statement. So this should be the same if we deform our space a little bit. So what if we deform our space by like stretching it out in this direction? So what will happen is the form, okay, so the vectors will grow, and so let's see, so this is what will happen for the vector picture. Because you're sort of stretching it out, so these vectors will grow much more. And then the form picture, what will end up happening is that the equivalent form, you'll actually sort of get something which is like the same length over here, but like something that's smaller on the top and bottom. And the reason is because if you have like a smaller thing paired with a longer guy, then you're going to get the same number as before. Does that make sense? So if you look at, so if this map is F, and this is F star d theta, this guy is going to be small. And again, you can think of that because like you're pulling back in this case. So going in this direction, F is going to be shrinking in this direction, and so that's why when you pull it back, the form is going to be smaller than the previous guy. So what I'm trying to say is that over here in this picture, this looks uniform. but in this picture it doesn't. Right? So what we're going to need is some sort of rigidity on our space to talk about uniformity at all. Right? Okay, so what is this form of rigidity? It's a metric. Okay, so the idea of a metric is that you have your tangent space at every point. So you have your manifold, whatever it is, you have a tangent space. And what this does is it puts in a product on ppm for every p, which is smooth. Okay, so what does this mean? This means that if you have two vectors v and w inside ppm, then you can, I'll use some different notations I guess from time to time, but you can do something like v comma w, or sometimes I'll write as g v w, and this will be some real number. And so this is just a dot product. And the way that you should think about this is that it specifies sizes of vectors. In particular, gives unit. So the way you think of a metric sort of is to say that it gives you a specified size on every plane. And so what this is doing is that this is sort of stretching things out. So this would not preserve the metric. So if you're looking at isometries, which are maps that preserve the metric, then this means that this will preserve size of vectors, which will mean that it will preserve the size of the forms. And so that means that it will sort of preserve this uniformity idea that we want. So in some way, we're going to want to tie this uniformity back to a metric. So let's see here. Okay, first thing I want to say is like, this is sort of like maybe the worst way to introduce a metric, because a metric should be introduced as something geometrical. So I will say that a metric forces shape of a manifold. And for example, let's say that you have a picture of some manifold where in your picture these are all unit vectors according to the metric, which I'll call G. Okay? But these don't look the same. So in order to get them to look the same, right, what you're going to want to do is shrink down these directions. So it sort of shrinks down the vectors out here. And so what this will mean is that in order to get these vectors to all sort of look the same size, you'll have to like impose this sort of curving of the shape. So in order for all the vectors to look the same, it forces the shape itself to curve it. So this is what I mean by the metric forces the shape of the manifold. So we won't discuss that right now, but like this is sort of what metrics are actually useful for. And we'll maybe discuss this later. Okay, so now uniformity. So the idea is that you want sort of minimize variation. Right, that's roughly what some uniform thing should mean. It should mean that it like doesn't change very much. So we know that differential forms means that you can integrate them. So if you have, let's say you have two things, two functions, which have the same integral. Yeah, so let's say that you have two functions which have the same integral, right? So clearly this one is more uniform, right? But how do you detect that's more uniform? Well, if this is like, let's say f and this is g, then the integral of f is equal to the integral of g, so that doesn't really give you much information. But what you could do is you can look at the integral of f squared versus the integral of g squared, right? And so what this does is it sort of, if this is f squared and this is g squared, then this sort of exaggerates differences. Let me spell that now. And so that means is that the integral of f squared is going to be less than or equal to the integral of g squared. Does that make sense? Yeah, I'm pretty sure you can formally prove that this is true using some sort of inequality, but Cauchy-Schwarz or something. So our goal will then be okay. So let's see. So we have like some omega class inside HK, right? And we want to find a uniform representative. So in order to do that, we're going to quote unquote minimize the integral over a manifold of the size of omega squared. Right? So what does this mean? Well, this is interesting because this is first off n-dimensional. So integrating and like this is something squared. This is like a k form, so this is maybe 2k form question mark. But we know we can't integrate 2k form over n-dimensional manifold. So what do we actually mean when we say that we're going to take something squared? So in order to define this omega squared, this is where we're going to need the metric. Okay, so here's the idea. Let's say that we write omega as the sum of omega I dxi. So we might think that omega squared should be sum of omega I squared, right? So this seems like a reasonable thing to do because this is like how you look at the norm squared of vectors, like Pythagorean theorem, whatever, right? But this is not invariant, or I guess I should say not invariant. It's not well defined because it depends on choice of xi. Right? It depends on the choice of your coordinates. So if you shrink your coordinates, for example, then the coefficients would grow. And so you have that the norm would change. So instead what you're going to do is you're going to say, okay, metric tells you that at every point you can take E1 through En, which is in orthonormal basis, right? And then you can take your dx1 through dxn, which is dual to this guy. So what we're doing is we're saying that these dx's in particular measure things of length 1. So now we're going to say that omega squared is equal to the sum of omega I squared with respect to the spaces, which depends on the metric G. So what this means is like even if you like stretch out your space by a factor of 2, right? So this will now change G, which implies that it changes the dxi, which means that if you then like, but what it does is it doesn't change sum of omega I squared with respect to unit basis forms. Does that make sense? So this will be how we'll define the length, and now we want to minimize this guy. Okay, so first off, size omega squared is a function on M. So what do we mean by the integral of omega squared on M? And so the answer is that over here, we're going to put a special form called the volume form. And so at every point, the volume form is defined as follows. The volume of V1 through Vn is the volume of V1 through Vn with respect to the metric. So one way that you can do this is you can say that the volume is equal to, you know what, maybe I'll do this. Maybe I'll put bars over these guys, which are the unit forms. And so the d volume is equal to dx1 bar up to dxn bar. So it says that these are unit things, and this will take in a unit cube, and it'll give you the value of 1. Or in general coordinates, d volume is equal to the square root of the determinant of g of dx1 to dxn. What does this mean? Let's say that this is dual to the vectors vi. So g as a matrix is then going to be vi vj. And you can show that this is like some matrix representing the n products of vectors, and you can show that the volume spanned by these vi's is equal to the square root of the determinant of this guy. So what this means that this basis is dual to the vi's means that if you do dx1 through dxn of v1 through vn, then this is going to give you 1, and so the scale factor tells you that you're going to actually get the volume of these guys. So this is how you define a volume form, and so we're going to want to minimize this. So maybe 5 minutes. Let me see how much of this I can get through. The goal is minimize integral over m of this guy with respect to the volume among omega such that d omega is equal to 0 and the cohomology class of omega agrees with the cohomology class of some fixed cohomology class. So what you're finding is the minimal representative inside this cohomology class, right? And so this will give us our special uniform representative. Cool. So how do we do this? So let me give you a quick calc of variations primer. So you know that if you, let's see, minimum of f of x implies derivative f with respect to x equals 0. And so to remind you why this works, it's that f of x plus a is equal to f of x plus a times partial f. And so if this guy is non-zero, then we can choose a to make a partial f less than 0. And so that'll mean that f of x is not a minimum. So let's just say if you displace a little bit, you can make it smaller. And so this is scalar land. In vector land, this says that f of x min implies gradient of f is equal to 0. And again, this is because f of x plus a is approximately f of x plus gradient of f divided with a. So same reasoning, if this is non-zero, then you can pick an a such that it goes down. So now we're going to talk about the function land. So let's say that we have some function like this, f of f. So this says that you plug in some function f and gives you a number. And so this is what we have over here. We have some function f, and then we're getting a number which is the integral of it. And so we want to minimize over all choices of f, this guy. So what this means is that we should look at f of f plus g, and this will be approximately equal to f of f plus we'll call partial f subscript f of g. And maybe I'll leave out the f later, but what this is saying is that this is going to be something which is sort of like a first order variation with respect to g. And again, the idea is the same. If this guy is non-zero, then you can sort of change it so that it's going to be negative, and so it won't be a minimum. By the way, if it's non-zero, then that means you can choose something, which means that a dot gradient of f, for example, is non-zero. So it could be either positive or negative, but if you flip the sign of a, then it would be negative, if the initial term is positive. Okay, so what we have here is something like the integral over m of size of omega squared. So if this is f. So del f, by intuition of, for example, like if we take x squared, then the derivative is going to be 2x. If we take like v squared, then the derivative is going to be like 2v. So this should be like the integral of 2 omega in some sense over m v volume. But again, like this doesn't really make sense. So in order to make sense of this, what we look at is like, what does this actually mean? This means that in vector land, if we look at f of v plus w, where f is equal to this, then this is approximately equal to v squared plus 2v dot w. So we have this dot product over here, right? And so what we should actually say is that this is saying that del f of eta is equal to the integral over m of 2 times some sort of inner product of omega dot eta v volume. Yeah, so I guess since now I'm probably out of time, I'll just sort of give some indication as to what we'll do next time. So the goals will be to define this inner product that gives norm of omega squared as omega dot omega. And so this will lead to something called the Hodge star. And then you want to minimize del f among omega such that e omega is equal to 0 and omega is equal to omega naught. And so we'll see that this leads to some condition which will lead to this guy, which is to be defined. D star omega is equal to 0. And if both of these conditions are satisfied, then we get a Hodge class. It's called like a harmonic form, and this will minimize. And then we'll see that n easily prove no. So I expected this lecture to take 2 lectures anyways, but this is the idea for what we will have next time. Anyone have questions on stuff for today? Any of this motivation? It's kind of an awkward place to end off, but